Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on July 31st, 2025, just yesterday. This paper introduces two AI systems that managed to fully prove 5 out of 6 problems at the 2025 International Mathematical Olympiad. The paper is titled Seed Prover, Deep and Broad Reasoning for Automated Theorem Proving, and as we'll see, the results are really impressive. The authors tackle a key challenge. LLMs struggle with theorem proving because natural language is often too vague. They solve this using a formal language called Lean, which provides clear, automatic feedback on whether a proof is correct. Also, the authors shared their repository on GitHub. In it, you'll find the code for 2 projects, Seed Prover and Delta Prover. They also include a fascinating breakdown of the results from the IMO 2025, showing exactly which problems the system managed to solve and formally prove. Alright, so to really put their achievement into perspective, the authors provide this great chart. It shows the progress of various AI models over the last few years on a benchmark called the Mini F2F test. This is a standard test set of math problems used to measure how well these systems can prove theorems. As you can see, performance has been climbing fast. But right at the very top, published in 2025, is Seed Prover, essentially hitting a 100% pass rate and completely saturating the benchmark. This visualization really drives home the leap in performance they've achieved. So, a key reason for that huge performance jump is a change in strategy, which this next figure illustrates perfectly. It compares the traditional whole proof with their new lemma-style approach. Instead of tackling a theorem in one single block, Seed Prover first generates and proves smaller intermediate steps called lemmas. Think of a lemma as a proven stepping stone. This modular approach is powerful. It allows the system to verify each piece independently, track progress, and even combine successful lemmas from different reasoning paths to solve much harder problems. Building on that lemma-style approach, this diagram shows the different inference settings, which are basically the strategies the model uses at test time. The light setting is a powerful iterative loop. The model tries a proof, and if the Lean compiler, the part of the Lean system that checks the proof for correctness, finds an error, the model summarizes what went wrong and tries again. The medium setting is even more sophisticated. It has an outer refinement loop for the main problem, but also an inner loop to specifically solve the tricky lemmas that caused the failure. This nested strategy allows the system to focus its computational power very effectively. And finally, for the absolute toughest problems, there's the heavy inference setting. This workflow is all about combining depth with breadth. It starts with a module called a proposer that generates thousands of conjectures, which are essentially educated guesses about potentially useful mathematical statements. Each of these conjectures is then tested using the light setting. The ones that get proven become new lemmas. From this massive pool, the system selects the most promising lemmas and uses them in the medium setting to finally tackle the original, difficult problem. Now, one area where the formal language Lean has limitations is geometry. So to tackle this, the authors developed a specialized system called Seed Geometry. And this table shows just how well that system performs. It's a head-to-head comparison between Seed Geometry and the previous champion Alpha Geometry 2 on geometry problems from the International Mathematical Olympiad from 2000 to 2024. Each row is a specific problem, with a checkmark for a successful proof. While the two are very competitive, Seed Geometry solves more problems overall, establishing a new state-of-the-art. Moving beyond geometry, this table really summarizes the overall power of the Seed Prover system. It compares its performance against the previous state-of-the-art across a whole range of formal math benchmarks, and the results are just staggering. On the Putnam bench, for example, it solves 331 problems, nearly 4 times more than the previous best of 86. It triples the score on the Combi bench. And on past International Mathematical Olympiad problems, it successfully proves over 78% of them. This is a massive leap forward across the board. So in conclusion, this work represents a truly significant advance in automated reasoning. It shows that the combination of large language models with the rigorous, verifiable feedback from formal systems is a recipe for success, tackling problems previously out of reach. That's it for this